Howdy folks, Mr. Hess here again with another geometry lesson. Today's lesson is 4.3 and it's titled Write a Coordinate Proof. Although the title says that, and we will show you a coordinate proof here, an overwhelming majority though of this lesson will really just involve the distance formula and finding midpoints and applying those concepts to real world situations, real word problems, you might say. Okay, so what I do want to do is start off though with a coordinate proof. Now, a coordinate proof is a little bit different than the two-column proofs that we were doing that had the statements and the reasons. On a coordinate proof, by definition, it's really just a proof that uses coordinate geometry, so coordinates on like an XY coordinate plane, along with some algebra to help you figure out the proof. So we've got a proof here that is actually a proof of the distance formula. You may recognize that right here where it says PQ equals this big square root, and that's the distance formula. Using the coordinates of the endpoints here, we can figure out that distance. But I want to show you then in this proof then where this formula comes from. A proof of why it works. Okay, and I think I might have shown you something like this once before, but anyways, I'm gonna proceed with this proof here. Okay, and one of the first things I'm going to do then is in my picture over here, I've got just some arbitrary segment I made up that has two sets of coordinates here, a point P that we call x1, y1, and a point Q that has x2, y2. And if I ever want to find its distance, this formula is going to work, but it's based on really the Pythagorean theorem. Because if I were to do this, if I were to drop a segment straight down this way and put one perfectly horizontal this way, do you see that I can make this into one big right triangle? Okay, in fact, the coordinates of this point right down here in the corner is, the x value of it, see how it's a 5 on here? Well, up here we have an x value of 5, so it has the same x value as up here. This x2 is also the same coordinate here. This would be an x2. And then the y value of this point, it's down here at -2, is the same as at this point over here. It was down here at -2. So the y1 is the same over here then. That's a y1, that's a y1. This is an x2, that's an x2. So it's stealing the x coordinate from up there and the y coordinate from over here. All right, now, since I made a right triangle out of it, that means that I'm going to be making use of the Pythagorean theorem, which you should already be familiar with, is a squared plus b squared equals c squared. Okay, so looking back over here then at my triangle, what I want to do then is figure out my A, B, and C on my picture over here. And if I were trying to find, for example, the length along this bottom side here, I want you to see that since our y1 stayed the same, the x values are really all we would need to use to determine how long that segment is. I would have to take the x2 ending value over here and subtract from it the y or the x1. If you don't believe me, use the actual coordinates here. See how this is at the coordinates 5, -2. And this one is over here at -3, -2. So if we had a segment running perfectly horizontal with these coordinates, since the -2 stays the same, all we really had to do was take the 5 and the -3 and subtract them from one another. So 5 minus the -3 creates a double negative plus positive. So that's 8 units. Or see it? 1, 2, 3, 4, 5, 6, 7, 8. So again, I get that distance really by doing this, by subtracting the two x values. Okay, so all this work was just here to kind of emphasize that and reinforce that. You don't have to put that part though. So I'm going to kind of erase that, leaving just going from this point to this point. You would simply subtract your x values. Okay, I'm going to do it again. See this leg over here that runs perfectly vertical? It's got an x2, y2 up here, but an x2, y1 down here. The x2s stay the same. So if I want to know how long that is, really all I'm going to do is just take the y values, y2 and y1, and I'm going to subtract them. y2 minus y1. And again, just to help emphasize it, if you look at the actual coordinates, remember this was at 5, -2. This one up here is at 5, 8. So if I was trying to find out how long that is, since the 5 stays the same, all I really have to do is look at the y values. It's all the way up here at 8, and then it drops all the way down to -2. You can find how long that is by subtracting those two from each other. If you take 8 minus the -2, you see plus positive, that adds up then to 10. And just to emphasize it, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so again, I got that by taking my y values and subtracting those. So I'm going to erase that work again, leaving just this length is y2 minus y1. This length is x2 minus x1. Okay, those two lengths, by the way, again, are the A and the B. They're the legs of my right triangle. Okay, so in my coordinate proof now, I'm going to take these two values and I'm going to plug them in for the A and B. And the last side here that I want to find, you see that goes from P to Q. So I'm just going to simply call it PQ. So PQ is going in for the C. So according to this, we would square it. And my legs, A and B are, well, you know, technically you could put in, just like I did here, the PQ, you could put in the letters, like if I call this point, let's say point T. You know, you could start by calling this QT for one leg and PT for the other one. But then again, now I'm just going to go ahead and replace those anyways. The QT was this one, right? So I'm going to replace that with the y2 minus y1. So it says take that and square it. Plus the PT I'm going to replace with this, the x2 minus x1. And again, it says square that. And this, I'm just going to leave as, for right now, just PQ squared. So I'm getting really close. You see this? I was trying to prove that PQ equals the distance formula right here. Okay, so all I need to do now is go from a PQ squared here to just a PQ. So in order to get that, I have to get rid of the square by doing the, yep, you guessed it, square root. So whatever I do to this side, I have to also do to this entire side over there. and the square root of PQ squared is just PQ. And then I would just recopy all this, which is, look, that. Okay, but, well, just to show you, you could flip-flop these too, by the way, since they're being added. So I'm just going to kind of flip-flop that up here. I should have put my PT here and my QT there. You know, the legs can be interchanged either way. So I'm just going to flip this around and put that back here in the front. X2 minus X1 and Y2 minus Y1 over here, and the whole thing square rooted. And so there you have it. See, there's a coordinate proof of the distance formula. Okay, so we don't do a whole lot of coordinate proofs, but I did want to show you one of those just to make you aware that they do exist. Okay, so now I want to go ahead and jump into some problems that you're going to see in this section, you know, types of problems you might see on your homework. Okay, so give me a sec here and I'll set one up. All right, as you can see up here on the board now, I've got a new problem for us to try. And I've got a triangle pictured over here, A, B, C. And they want to know, are any sides of the triangle congruent? Remember, congruent is just a fancy way of saying that they will have the same length. Okay? Congruent means that you should be able to literally take one segment, put it over top the other, and you'll get a match, you know, on the length. So really, I'm just asking then, do any of these sides have the same length? Well, we could determine that the lengths of these sides, though, using that distance formula that we just mentioned a second ago, the one that we proved. So the distance formula, remember, looks like this. Square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so we're going to have to use this not once, not twice, but 3 times, right? We got to check all 3 sides. So if I wanted to start by finding, for example, the length of AB, then I would be plugging in my coordinates for A and B into the formula. Let's focus first on the x values. So we have a -2 and a 3. If I call that my second point, then I can just go 3 minus -2. And don't forget to square it. Over here, the y values. So I went 3 minus the -2 here, and then for the y values, I'm going to go 6 minus the -2 there. Don't forget again to square it. So these both create double negatives that become plus positive. 3 plus 2 is 5. 5 squared is 25. 6 plus 2 is 8. 8 squared is 64. Okay, if you add those together, do you see you get 89? So AB's length will be the square root of 89. You could go on a calculator even and find the decimal version of that. But for right now, I'm just going to go ahead and leave it just as square root of 89. That way I don't have to do any rounding. And it'll be pretty easy to determine if I have any other matching sides, because if they are the same length, they should come out to the same square root. Square root of 89. Okay, but since we're just checking for ones that match, there's no need to actually convert that to a decimal. Okay, now we got to do that again. We got to check, for example, BC. So I'm going to start over again. This time we're doing BC. So we're going to be using the coordinates 3, 6, and 8, -2. Okay, so my x values were 3 and 8. I'm going to subtract the 2 of those, like it says here. So I'm going to go 8 minus the 3. Don't forget to square it. And do the same for the y values. So I went 8 minus the 3. I'm going to go negative 2 minus the 6 for my y values. Again, don't forget the little square there outside of the parentheses. 8 minus 3 is 5. 5 squared is 25. Negative 2 minus 6 is negative 8. When we square a negative times a negative would be a positive, so it'll be positive. And then 8 squared is 64. 25 plus 64 is 89. And oh, look, we get the same result. You see that? This is also square root of 89. Okay, let's check our last side and see if it matches as well. Now the last side, I hope you see, you really don't even need the distance formula for, since it runs perfectly horizontal here. You could even just look at it and count. You go, oh hey, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one has a length of 10. Okay, the square root of 89, by the way, is not 10. Okay, because, just to kind of prove my point, the square root of 100 would be 10. So that's not a match, is what I'm trying to emphasize. So I only have 2 matching sides, which, by the way, do you know what kind of triangle they call that when you have 2 matching sides? I bet you do. A lot of people have heard of this name. Starts with an I. Yeah, isosceles. This is what we would call an isosceles triangle. Isosceles. Okay, so, long story short, some of the problems on your homework are going to involve using the distance formula to find side lengths and see if you have any matching side lengths, any congruent sides. Okay, so I'm going to show you another type of problem here next. All right, our next type of problem here is asking us to find the length of a segment of a line y equals 3x minus 6 from x is negative 3 till x is 4. If you remember correctly, we did a previous problem in a previous lesson where we made a quadrilateral and it had domain restrictions on it where instead of doing a full line, we had cut it down to from this x to this x. Okay, and that's what's going on here. If you actually graph the full line, y equals 3x minus 6, it would cross the y-axis at negative 6. So it would cross down here. And it would have a slope of 3 over 1, telling us to go up 3, forward 1. So 1, 2, 3, forward 1, 1, 2, 3, forward 1. You can keep doing this, making more and more points like this. Okay, and then that would be a full big line that runs along there, hitting all these key points that I just made earlier, hitting all those key points. Okay, but then we have a restriction we're putting on the domain here. We're saying that the x values, we're only going to graph, instead of the full line, we're only going to graph from x is negative 3 till x is positive 4. Okay, well, x is negative 3, if you follow that down far enough, this line would keep going and going and going until eventually, at x is negative 3, there would be a point down here, clear down there. Okay, that line would keep going, but I'm going to restrict it. We're going to shorten it up. And we would say, okay, one end of it's going to start clear down there. And then the other end of it's going to go clear up until you get to an x value of 4. So if you follow 4 all the way up, it hit right there. X is 4, so you'd stop it right there. So there's our segment. Okay, and we're trying to find the length of that. Okay, so you need these coordinates. at each end here to find the distance or length. Okay, now normally you wouldn't graph this, so you wouldn't be able to look up here and steal these coordinates. You know, like see how that's at 4, 6. So this end of it I already know is at 4, 6. This one down here, it went so low, it's kind of hard to figure out where that one hit down there. But normally, again, I wouldn't even bother to graph it. What you could do is, to figure out this set of coordinates and this one down here, is simply take this equation for the line, y equals 3x minus 6, and plug in your x values. So we're going to take this x value and plug it in and see what we get. So we'd have 3 times negative 3 minus 6 equals our y. So 3 times negative 3 is negative 9. Negative 9 minus 6 is negative 15. So when x is negative 3, when x was at this, we're finding the coordinates right now, this point down here, see? When x was negative 3, this went clear down here to negative 15. There's your y value. So there's your coordinates. This one is negative 3, negative 15. And then just to show you that I was correct up here with the 4, 6, this time I'll take the same problem, and instead of plugging in the negative 3, let's plug in now the positive 4. So if I put a 4 there, 3 times 4 would be 12. 12 minus 6 would be 6. So 4 was the x value, y was the 6. So 4, 6 is my coordinates, just like I had labeled up there. Okay, so that would be the first thing on a problem like this you would do to figure out these endpoints, is plug these x values into here. Okay, and get these coordinates. Okay, now that I have the coordinates, now I'm going to erase this so I got some room to work with here. Now I plug everything into the distance formula. x2 minus x1, y2 minus y1, and then don't forget to square them and add them and do the square root. Alright, so let's plug it in. I got x values of 4 and negative 3. So I'm going to subtract them. 4 minus negative 3. Square it. Plus. Now let's do the same with the y values. I've got y values of 6 and negative 15. So I'm going to take that 6 and the negative 15, and like it says here, subtract them and square them. Alright, I've got double negatives here, double negatives there. 4 plus 3 is 7. 7 squared is 49. Plus 6 plus 15 is 21. 21 squared. That's too big for me to remember here, although I should know this one. I want to say 484, but I don't think that's right. 441, that's what it is. 441. Take that 441, add it to the 49. Now we're up to 490. So the length of this segment would be the square root of 490. If you want to know what that is approximately as a decimal, then punch that into your calculator. Square root of 490 is about 22.1. 22. If you go out to the 100th, it would be 22.14. Okay? So there you have it on a problem like this. If they give you a line and they restrict the domain on it, restrict the x values, it'll shorten it up into a segment that you can now find the length of. Okay, let's try another type of problem. Before I show that next type of problem, I want to remind you about our midpoint formula, which we're going to utilize in this section as well, this module, this lesson. And in the midpoint formula, we find our x coordinate of our midpoint by averaging the x values of the two ends. You know, like if this is my segment with a point x1, y1 here and another point over here at this end that is labeled as x2, y2, the dead center middle, the midpoint, is found by averaging the x's, averaging the y's. Remember, an average takes two values and finds the exact middle. You know, if this end is over here and this end's over here, you take these two values and average them, you're going to find the dead center middle. Okay, just to kind of illustrate that point, I'm going to do this like we did with the Pythagorean theorem. Remember when I made this into a right triangle like that? Okay, so this down here, you see, is representing movements from side to side, like x values run. See how the x values run that way? So essentially, when we do an average like this, what we're really doing is finding the middle of this one. See how this goes from -3 at this end. Your x values here is -3, and at this end, it's a 5. So if I'm going from -3 to 5, the dead center middle of this would be, if I just keep working my way in, look, 1, 2, 3, 4, right there. Right there is the dead center middle of these x values here. Okay, and if I keep following that, then again back up, right there should be the new x value of the midpoint as well. And then we're doing the same thing over here. See how this runs from a +3 all the way down to a -3. So if you work your way into the middle of this one, you see the middle of it would be right there, 3 units in from each end. You know, if you follow that one, again, if I go in this way, see how it hits again right there? So I'm finding the middle of the y's, the middle of the x's, and when I follow them together, that'll be the dead center middle of that segment as well. And again, to find a middle, to find the exact middle of anything, you just do the average. So we're just averaging the x values, averaging the y's. Okay? So keep that in mind, that midpoint formula for this next problem that I'm about to show you. Okay, our next problem is one I'm taking right out of the textbook here. It's on page 127. But if you read through this here, we're going to apply, it says the distance formula, and we're also going to apply the midpoint formula to this problem as well. But they mention that a ship is traveling along the line y equals 1.5x plus 20 from a port located at x equals 0 to an anchor point along the same line 30 nautical miles horizontally from the port. So again, just to emphasize what they said, they have a ship that's going to travel along this dashed line here. It's going from the port out here to the anchor point. Okay, and then they mention that the port here is located where they're going to call an x value of 0. So that's going to be ground 0. X is 0 there. And the only thing they tell you is that as it travels along this line, which is represented by this equation, that you're going to travel sideways a nautical distance here of 30 nautical miles. Okay, so that's not the length of the dash line. That's the length of this horizontal line going across till you get to this point, which is going to line up with the anchor point if I were to drop a line straight down. Okay, but on this graph then it says 1 unit is going to represent 1 nautical mile. Okay, And approximately, they want to know approximately how far does the ship travel, and what point represents half the distance traveled. Okay, so they want to know the full length, how far does it travel, and they want to know what point where would the point be located where you would be at in the dead center middle. Half the distance traveled is represented by what point. Okay, so I'm going to do this same problem only on my dry erase board here. So I'm going to set up a picture here. All right, so here's my picture again representing the scenario they were talking about, where here's port. The ship's going to travel this distance here to the anchor point out here. So I call it port P and the anchor point A. And as you travel that, you're going to move. You're going to be moving on this line, but you're going to be also moving at the same time as you travel a horizontal distance of 30 nautical miles. Okay, so one of the first things I want to do here then is just go ahead and drop a line straight down, kind of make this into a right triangle. And I want to emphasize that the path we're traveling from P to A is represented by the equation. They had mentioned that earlier. The equation y equals 1.5x plus 20. And then they also mentioned, remember that port here, where we started at, they're going to kind of call it our ground zero, so to speak. So we're at this point, x is 0. Okay, so this is really similar to a problem we already did earlier in this lesson. Remember when I graphed a full line, but then we restricted the domain? Okay, that's what we're doing here. If this is 0, if x is 0 here, and if I travel 30 nautical miles this way, do you see that your x value at here would then be 30? You know, you went from 0 to, and you went 30 nautical miles this way, so that if that's 0, that's 30. Okay, so what I really need to do now is find the length of this segment that is a portion of that full line, but it's only running from x values from 0 to 30. So if you remember right, when we did the problem similar to this one earlier, which was not a word problem version, but it was just, it flat out said, here's the equation, find the length of the segment that only runs from, say, 0 to 30. But if you remember right, on that problem, we took this equation, we plugged in 0 for our x value right in here. So if I plug a 0 in there, I can then find the y value. So what's going to be 1.5 times 0 plus 20? Well, anything times 0 is 0. 0 plus 20 is 20. So there's your y value. When x was 0, y was 20. So you could say the coordinates at this point then is 0, 20. Because earlier all I knew was the x value was 0. I had to plug it in, see, to find the y. And I'm going to do the same thing to find this one up here. I know the x value of it is 30, but let's find the y value that goes with that. So this time, instead of plugging in a 0, we're going to plug in a 30. So we're going to take 30 times 1.5. Let's see, that's 45. And then add that to the 20 and you get 65. So the coordinates at this end now are at 30, 65. Okay, I went through that trouble to find the coordinates because now that I know the coordinates, now I can plug in these coordinates into the distance formula to find the length. Okay, so here, I think I can squeeze it in down here. Remember, the distance formula looks like this. So if we plug in 0 and 30 for our x values, I'm going to go 30 minus the 0 just to avoid some negatives. And do the same with the y values. So instead of 30 minus 0 for the y values, I'm going to take 65 minus 20 and square that. Well, 30 minus 0 is 30. 30 squared is 900. $65 minus 20 is 45. 45 squared is a pretty big number. Let's see, 45 times 45 is 2,025. Add these together, so plus another 900 yet, gets me up to the square root of 2,925, which is approximately, let's figure out the decimal here now. Square root of 2925. It's approximately 54.08 if you go to the nearest hundredth. Okay, so while this was 30 nautical miles, we just found this from P to A to be about 54 nautical miles. So that length is 54.08. Now there was one additional thing they wanted you to do on this problem. Not only did they want you to find that length PA, but remember they also wanted us to locate the midpoint. They wanted us to figure out where would you be at if you're in the dead center middle of that segment PA. Okay, and they're looking for the coordinates, you understand? Not the distance. You know, the distance would just be half of that, right? You know, if that's a midpoint exactly in the middle, the distance would be half of that. But I wanted to know the coordinates. So for this part of the question, we don't need this equation. You know, we don't need to know a whole lot other than these coordinates of the endpoint, because we could simply then make use of the midpoint formula, which we know is x1 plus x2 divided by 2. That's your new x value for the midpoint. And y1 plus y2 divided by 2. That's the new y coordinate. So if we plug into there for this, we're going to use 0 and 30 for my x values. So I add them and divide by 2. 0 plus 30 is 30. 30 divided by 2 is 15. We do the same with the y values. See the 20 and the 65? We're going to add them and divide by 2. Well, you add them, you get 85. And half of 85 is 42 and a half. So this midpoint right here is located at the coordinates 15 and 42 and a half. Okay? You're going to have some word problems on your homework as well, where you'll have to understand if you need to apply the distance formula, for example, or maybe a midpoint. Okay, but I assure you all the word problems will involve one or the other or both. Like this would involve both distance and midpoint. Okay, but I've shown you enough that this should prepare you then for your homework. So I'm going to end my lesson.